Here's the answers to the quiz on properties of metallic and ionic bonds. So here in number 1 and 2, we are looking at Coulomb's law again. It never goes away. We can use Coulomb's law to gauge the degree of attraction between any oppositely charged particles. Coulomb's law is an equation, although we don't have to calculate anything with it, but it's kind of that comparison of Q1 times Q2 over R, where Q1 and Q2 are the charges, and then R refers to distance. And so anytime we're looking at the degree of attraction between two oppositely charged particles, we look at the magnitude of the charge. The higher the charges, the more strongly they'll be attracted to each other. And then we look at the distance between the two charged particles. We want this one to be small. If I've got charged particles that are really close to each other, that should show a stronger attractive force. And so obviously we can use this in comparison of like the nucleus versus the electron cloud, and we can then judge things like radius and ionization energy. But we can also use it with ionic compounds, and it eventually helps us to predict properties like melting point. So in question 1, using Coulomb's law, predict which ionic compound will have the highest melting point. And so melting involves separating the particles if we're going from solid to liquid. And so if I'm looking for a high melting point, that means that it melts at a high temperature. So I would think then that the particles are very strongly attracted to each other if it takes a lot of energy to separate them. So between sodium chloride and magnesium oxide, I want to know which one would have the particles most strongly attracted to each other. And it should be the magnesium oxide. The number one thing we look at is magnitude of charge. And so if I've got my magnesium oxide, we'll make this a little smaller. Magnesium is a +2 ion, and oxygen is a -2, but sodium is only a +1, and chlorine is a -1. So with ionics, the number one thing we look at is magnitude of the charge. If you've got higher charges, then you're going to have a stronger attractive force. It's going to take more energy to separate the particles and change phase. Now, when you get to the second question, if I'm thinking about charge again, and I look at potassium and chlorine, -1, sodium is a +1, fluorine is a -1. Okay, so we check the charges, and if they have the same charges, then I look at the distance between the ions. Or in other words, I'm looking for smaller ions. Smaller ions can pack more tightly together in the crystal, and then it's going to take more energy to separate the ions. So all I have to do is think about periodic trends now. And I look at potassium versus sodium. Sodium is smaller. It's only got electrons in 3 energy levels versus potassium's 4. And then I kind of do the same thing. Fluorine and chlorine are in the same group, but fluorine is smaller. So both the sodium and the fluorine are smaller. So if they're smaller ions, they'll pack more tightly together. And you could get a situation where it would be hard to predict qualitatively. Where, like, what if you had higher charges but bigger ions? And then we might have to resort to calculations to figure out the exact strength of the attractive forces. But you don't have to worry about any of those. Anything that you'll see, you would be able to compare melting points qualitatively without doing any calculations. And so obviously, yeah, there could be times where you could have opposing forces, and then it would be hard just to predict without numerical data and calculating the degree of attraction between the particles. But you won't see anything like that. You'd see something kind of like this. And when you get to the summative, you'll see the same kind of question. It's just not multiple choice anymore. It's just that now I would have to explain which has a higher melting point. So the number one thing I look at is magnitude of charge. If I see higher charges, that's the stronger attractive force. If the charges are the same, then I look for the smaller ions, and it'll really just follow the trends on the periodic table. All right, so then some properties of ionic compounds are that they do easily dissolve in water for the most part. And we'll look at this a lot more later in the year, in that water molecules also have a charge to them. That the oxygen in an H2O molecule is kind of negative, and the hydrogen end of a water molecule is kind of positive. And so if you've got charged regions on a water molecule, they're attracted to the charged ions in an ionic compound. And then that attraction will help to kind of remove the ions from the crystal, so that in a solution, let's say I have a beaker. Oh, that's a good beaker. It's filled with water, and I put in sodium chloride. I add salt. Eventually, the sodium ions and chlorine ions just separate from each other. Minus, and they just kind of swim around, positive, minus, as individual ions. Now this is a physical change. All we did was separate the ions, where originally, positive, negative, positive, negative. Here might be the ionic solid, where the ions are packed real tight, but now I've just separated the ions with the assistance of some charged water molecules, and the ions just swim around in the water. But if you evaporate the water, now the little charged ions will suck back into the original crystal lattice, where they'll all kind of align perfectly, oppositely charged particles in the crystal, positive, negative, positive, negative. And so yes, most ionics do dissolve very well in water, which then kind of brings us to the next question. In order to conduct electricity, you need moving charges. Key word may be that they have to be moving, and I guess charged as well. Okay, so which of these would not have moving charges? The answer is the ionic solid. In the ionic solid, you've got the charged particles, but they can't move. They're packed real tight, and they're held together by what they call electrostatic attractions, which really is just a fancy way of saying attraction of oppositely charged particles. I mean, I could add another layer to my crystal. Negative, positive. I mean, that positive ion in the middle there, that guy's not going anywhere. He's totally surrounded by negative ions. And so in the solid, yes, we have the charged ions, but they don't move. So if you take like a conductivity tester and you plunk it in some solid salt, it's not going to do anything. It will not conduct electricity. But it will if you can make those charges move. So the two options would be either to melt the ionic solid, which, to be honest with you, is kind of hard in the lab. Most ionic solids have pretty high melting points. And in fact, soon we'll try that. I'll go in the lab and I'll try to melt some salt for you. I'm not usually very successful. And ionic compounds involve really strong attractive forces. These oppositely charged particles are very strongly attracted to each other. So it's hard to melt ionic solids, but it's not impossible. And some of them do have a little bit weaker attractive forces, and you can melt them, which then, if they're in the liquid phase, liquid particles can move and flow. And so then, yep, I could have moving charged ions. The other option would be to dissolve the ionic compound in water. Because now if I think about like my picture with the beaker and the ions, those ions are separated from the solid and they are free to move. So either melted in the liquid phase or in solution, meaning that they're dissolved in water. Those would conduct electricity, but not the solid. The ions cannot move. And then finally, our metals. Which of the following most accurately describes metallic bonding? And so we think of it as kind of this sea of positive nuclei surrounded by free moving valence electrons. So it's kind of ionic in the sense that we do have these positive ions because the metal atom will give up electrons. It's willing to lose electrons. All metals form positive ions. They want to lose electrons to obtain that full outer shell. But the electrons don't really go anywhere. They're not like distinctly transferred from the metal to the whatever it is. The electrons just kind of freely move amongst all the positive nuclei. So you've got these electrons that really don't belong to any one particular positive nuclei. They're just kind of free floating and moving amongst the metal. Positive and negative ions held together by strong attractive forces, and that makes me think ionic. Neutral atoms, like packed in a crystal structure. Well, they're not neutral. They do lose electrons to form a positive charge, and I don't know if I'd call it a crystal structure. Crystalline usually means like very organized, rigid crystal pattern. But from this last question, we do know then that this structure of metals is what allows for a lot of the unique properties of metal, that they're malleable and ductile. Ductile means that we can draw it into a thin wire. Malleable means we can pound it into a thin sheet. Well, yeah, that's because if I take a hammer to this picture of a metal, it's not that the positive nuclei are in a very rigid structure. And if I smash a crystal of salt, it's going to break and it's going to cleave. But here, those nuclei can respond to a change in force, like a hammer, and they'll just move. And they can because they're just kind of floating in this sea of electrons. So the nuclei can move, which then makes it possible to change shape. And because we have these moving electrons, then we can conduct electricity. Duh, obviously, metals conduct electricity, right? But it's because of this sea of electrons model where you have moving electrons. But obviously, metals don't all have like low melting and boiling points. And in fact, they're usually pretty high. And you've got a lot of attraction going on in a metal. You've got these positive nuclei that are totally surrounded by electrons. And so while, yeah, we can melt metals, but it's at a really crazy high temperature. There's only one metal that I can produce in the molten state in our laboratory, and we'll do that second semester. It's going to be great, but it's at like 1,000 degrees. It's insanely a high temperature. Yeah, overall, we think ionics and metals have really strong, really high melting and boiling points. And it's because the particles are charged, and charged particles creates a strong attractive force. Even though here in the metal, those charged particles can move and flow amongst one another.